I don't think I have the functions to share. Actually emailed her and told her I was like watching videos, so she has sing with the function like formula sheets that she made, and I started to send them all formula sheets. So I can send you those.
All right, so it's time to go ahead and begin.
Anyway.
So today, we're going to start talking about sequential circuits. So, everything we've discussed prior to today has been combinational circuits, which they also called combinatorial. And I mentioned, I think a couple of times, but it might have been a while. I mentioned something that combinational, the logic circuitry we've been looking at so far doesn't have, like it has no something. Remember what that something is? What is it? Memory, exactly. Yeah, combinatorial or combinational. Combinatorial and combinational are have the same meaning here. And it's logic circuitry that does not have memory. And if you don't have memory, you do not need a clock signal. Okay, see, when you have a sequential logic circuit, it does have memory. And when you have memory, there is a clock signal. So it's very easy to determine just from a structural diagram, a low-level diagram, like the one I showed you a couple of weeks ago with the microprocessor that you build in CP233. It's very easy just by looking at that diagram to tell whether a module is sequential or combinational, because if it's sequential, it's going to have a clock signal. It's going to have a clock input. And if it's combinational, it's not going to have a clock input. Now, a definition of a combinational type of circuit, and here's a general high-level black box diagram of any sort of combinational, abbreviated COMB here, where I'm showing you can have as many inputs, as many outputs as you want, as many or as few as you want. And when you have a combinational circuit, the outputs only depend on inputs. Like all the logic circuits we've looked at thus far prior to today, they just had some inputs, sometimes just a couple inputs, sometimes maybe 3 inputs, and then one or 2 outputs, and those outputs just depended on those inputs. When you have a sequential circuit, well, you can have as many or as few inputs, and you can have as many or as few outputs. But the big difference is when it's sequential, you need at least one output that feeds back to an input. Okay, so you have to have what we call feedback. And feedback is just a connection from an output back to an input. So the outputs of a sequential circuit depend on both inputs and outputs. Depends on both inputs and outputs. Okay, so those are the differences between sequential and combination. All right, so why is memory important? Okay, well, the reason why memory is important, or one of the reasons, and this is a big reason, and I'm going to be very general at this point, and we're going to get more specific as the quarter goes along, and then also in your future classes you'll get specific. But in general, if you have some sequence of events, all right, and again, being very general, let's say, you have some event A, an event B, event C, event D, event E, event F. And let's say there's a particular sequence between these events. Like if you're at A, from A, you go to B. And if you're at B, you go to D. You know, if you're at D, you go to E, and so on. You know, there's some sequence to these events. Well, in order to accomplish something like this, you know, some type of circuitry, you have to remember what event you're at in order to know which event you're going to, right? If I'm going from A to B, I have to be aware, I have to remember that I'm in event A, you know, and likewise, if I'm in event B, and I'm going to D from that event, well, I have to know where I'm at before I know where I'm going. Okay, and memory is required for that. Memory is required to know where you have been. Okay. Like I said, very general, but we're going to get more specific as we go along here. Okay, so feedback. The first, you know, more detailed thing that we're going to look at that has to do with this is what a latch is. Okay. Now, when we were talking about signed binary numbers and two's complement, remember how I said, or we learned that there's two meanings to the word two's complement or the phrase two's complement. You know, one meaning is two's complement as a noun, and that's just a listing of what values you can get from, you know, say 4-bit two's complement, like it was on that handout I gave. But then there was the other meaning when you take the two's complement, right? The meaning of two's complement as a verb. And do you remember two's complement as a verb, like what the result of that is? Like if I take the two's complement of some signed binary number, what am I going to get? What happens when you take the two's complement of a two's complement number? What's that?
You get the negation.
Right, exactly. Remember, that's how you negate a value, right? You take the two's complement of a positive binary number, you get the negative, right? You take a two's complement of a negative binary number, you get a positive, right? That's the whole thing behind doing subtraction by addition with signed numbers, right? That we talked about. Well, there's a similar thing with the word latch. It has two meanings depending on whether you're using it as a noun or a verb. Latch, the noun, is a logic circuit like this. Okay, this is called a NAND latch because it's made out of NAND gates. Latch, the verb, means to store or to hold, to remember, any of those. Okay. So if you look at this NAND latch circuit, it's got the two NAND gates, and then S and R, these are inputs, and Q and not Q, these are outputs. And you see how the Q output goes to the input of this bottom NAND gate, and the not Q output goes to an input of this top NAND gate. So you see that's feedback, right? Because an output's going back to an input. And specifically, we call this kind of connection cross-coupled. Okay, so you know, we would describe this as cross-coupled NAND gates. Okay? And if you cross-couple NAND gates, you get a latch. You can also have a cross-coupled NOR gate latch, where it's the same, you know, configuration, except you have NOR gates instead of NAND gates. Okay. So what we're going to do next is we're going to come up with two truth tables. Okay, we're first going to come up with this truth table that has 3 inputs and an output. And then after we have this, or once we get this truth table, we're going to condense it a little bit into this one where we just have S and R on the input side and Q plus on the output side. This diagram right here, this is the actual circuit for the latch. Right, so this is the actual. This diagram up here, which shows the NAND gate, and then there's this block that has TD. TD stands for time delay. Okay, so you know this diagram doesn't represent something you could actually build, right? It's can't build like a time builder. But what this diagram is for, it's just for analysis purposes. Okay, so this is the actual circuit you would hook for what, you know, Movado would build if you wrote the code for it, Verilog. This is just used to do analysis. Now, you see we have Q and Q plus. Q, and Q is an output. Q represents the present state of the Q output. Okay, and Q plus represents the next state of the Q output. Okay, so Q is what the Q output is now, and Q plus is what the Q output is going to be later. Okay, and in this analysis circuit, Q plus is right here, and Q is here. See, so you know, Q, it's the same output, and they only differ in time. Okay, so that's why the one is, or one of each is on each side of the time domain, right? Because they're only separated by time. Okay. Okay, so the next thing before we analyze this this NAND latch is just to remember, you know, the NAND gate truth table. So first of all, you should be able to tell me what the output of this NAND gate looks like.
1 0
Say that again.
1 0
One. So you're saying this one here
0.
and all zero?
Wait. 1 1 0. So
Yeah.
3 ones in there.
3 1 6. Yeah, you got it. Okay. 3 1 6. Right? A NAND gate, you only get a 0 out if all the inputs are 1. Remember, a NAND gate is the same thing as an AND with an inverted output, right? So an AND only gives a 1 out when all the inputs are 1. So a NAND just is the same except the output's inverted, so you only get a 0 out. Okay. All right, so just like at least 2 other times, we're going to understand this truth table. Right? Remember how I said that it's important to understand truth tables? And here what we're going to do is kind of split the truth table in half and then just look at each half separately. Like we're just going to look at the top 2 rows first and see what the top 2 rows tell us. So can you see what the top 2 rows tell us? What can we gain from just looking at the top 2 rows? Yeah, if one of the inputs to an AND gate is a 0, it doesn't matter what the other input is, you're going to get a 1 out, right? So only one input to the NAND gate has to be a 0, and I know the output's a 1. I don't even care what the other input is, right? Okay, that's what the top 2 rows tell us. What does the bottom 2 rows tell us?
There's 2 1s and 0.
Say it again.
Both inputs are a 1 and it's a 0 output.
Well, I can get a 1 output here.
Yeah, only if both inputs are 1, they can be a 0.
Oh, well, that's true, but that would be true for the whole table too. I'm just saying if you're just looking at those 2.
E is 1, then you go 0.
Well, I mean, here would be A is 1, but we could switch them around. Okay. Q is not B for what case though? But you're missing one part. I mean, you can see that there's an inversion between the output and B here, but what else? Oh, there we go. Yeah, see the bottom 2 rows are telling us if A is a 1, right? If we make one input to an AND gate a 1, the output's going to be opposite the other input. Okay, so you see the top row tells us if one input to a NAND gate is a 0, we get a 1 out no matter what the other input is. The bottom 2 rows tell us if one input to an AND gate's a 1, the output's going to be the opposite of the other input. Okay, does that make sense? So by understanding this truth table, when you do the analysis of the circuit, it makes it easier. You can do it in less steps, right? So let's go ahead and come up with this truth table here. Now, notice that in this truth table, we're going to use present state of Q as an input. The only output we have here is the next state of Q. So we got S and R along with present state of Q as our input. So there's 3 inputs. So how many rows in this truth table? 8, right? Because 2 to the 3. Okay. So all of these could be 0, or we could have 0, 0, 1, or we have 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and all ones. Right, so 2, 4, 6, 8, and in binary 0, 1, 2, 3, 4, 5, 6, 7. Okay. All right, now we're just going to go row by row. So the first row, S is 0, R is 0, Q is 0. And the output I'm looking for is the output of this NAND gate right here, right? I'm trying to find what this Q plus is, the next state of Q. Well, can you tell me what it is? Without doing nothing else here, because S is 0, so it's got to be a 1, right? Because like we said before, if one input to an AND gate is a 0, the output's going to be 1 regardless what the other input is. See, I don't have to find that other input because I already know this is going to be a 1. If I didn't understand the truth table of an AND gate, I could figure that out just by following the bits, but yeah, saving time because I understand the NAND gate. Okay, so yeah, next state of Q would just be 1. In fact, can you see that for the first 4 rows, Q plus is going to be 1? Because for the first 4 rows, S is 0, right? It doesn't matter if, this stays 0 and this goes to 1. This is still going to be a 1 because S is still 0. And, for the next row, when R is 1, Q is 0, Q plus is still going to be 1 because S is still 0. Right? As long as S is 0, Q plus is going to be a 1. I don't have to figure out the rest. All right, so you see the first 4 rows here, Q plus is 1. All right, let's go to the 5th row right here. Okay, now S is 1. Right, so for the last 4 rows, S is 1. So since S is 1, I need to find this other input, right? In fact, whatever that other input is, Q plus is going to be the opposite. Right? And again, that comes from the bottom 2 rows of the truth table. Okay, so let's see. For this row here, Q is 0, R is 0. Okay, well, because R is 0, what can I say about this output? It's a 1. See, I don't even have to know what that is now. This input's connected right to Q, so it's going to be the same value, but I don't necessarily have to know that because once one input of an AND gate is 0, I know its output is 1. So what does that make? I'm going to make Q plus 0. Okay. So we get a 0 here. All right, the next row, R is still going to be a 0. Right? So that's going to keep this a 1, and it's going to keep P plus a 0. Okay, then the next row, what do we have? We got S equal to 1, R equal to 1. So since R is equal to 1, we do need to know that other input. And Q is 0. And since Q is connected right to that input, that's going to make that input a 0. So what do we have? We have a 1, right? That's going to make this a 1 and keep Q plus a 0. Okay, now what do we have? S is 1, R is 1. The only thing that's different now is Q is a 1. That's going to make this a 1, which is going to do what? Make this a 0, which is going to make that a 1. Okay. So any questions on what I just went through? I mean, Do you see the value of understanding the truth table, right? Because it saves you some work, right? You don't have to do it by brute force. Okay, so the next thing we're gonna do is we're gonna take this truth table of 8 rows and make it into a truth table of 4 rows, just to condense it. And the way I'm gonna do that is I'm gonna parse this truth table in fourths. Okay, every 2 rows, I'm gonna parse it. And I'm first gonna look at these 2 rows. Okay, I'm gonna look at these 2 rows, then these 2, and then these 2, and then I'll come back to this because there's something peculiar about these 2 rows that we'll get to, and I want to save it for last. Okay, but let's look at these 2 rows right here. For these 2 rows, S is 0, R is 1. And you see what these 2 rows are telling us is that when S is 0 and R is 1, it doesn't matter what the present state of Q is, the next state of Q is going to be a 1 regardless. Okay, but you see, I can just write next state of Q is going to be 1. I'm not including Q because it basically drops out. Now, when you have this case where next state of Q is 1, we call this the set condition. And we say that the latch is set. And what's really important, because this is a common misconception that a lot of people make, is that this term set just refers to the value of Q plus. It doesn't correspond, or it doesn't relate to the input value. I mean, in this particular case, in order to get Q plus to be 1, S has to be 0, R has to be 1. That's for this latch, this NAND latch. But you can make a latch circuit out of NOR gate, like 2 NOR gates that are cross-coupled. And if you did that, you would find that there's different input values that get Q plus equal to 1. So when we say set, we're just talking about Q plus being 1. Okay, we're not saying that set means that S is 0 and R is 1. That's just what it happens to be for this latch. Okay. All right. So now if you look at the next 2 rows, these 2 rows, S is 1, R is 0, and it doesn't matter what present state of Q is, next state of Q is going to be 0. And this is called reset. And again, reset means next state of Q is 0. Okay, now these 2 rows. These 2 rows is why this circuit exists, okay? This circuit exists because it has the property of memory. It can store data. Okay, specifically, it can store a bit. So look, the last 2 rows, both S and R are 1. If the present state of Q is 0, the next state of Q is going to be 0. If the present state of Q is a 1, the next state of Q is going to be a 1. So you see, when S is 1 and R is 1, next state of Q is just going to equal present state of Q, which means the Q in the future is just going to equal the present Q. Well, that means you've retained a previous bit value, right? Because if it's 0 now, it's going to be 0 later, right? If it's a 1 now, it's going to be a 1 later. So you've retained previous bits. And by this time in the course, you should be aware that bits represent data, right? Bits are part of binary numbers, or, again, the 0s and 1s can represent anything we as designers want them to represent. So you see, this is called the storage state or the hold state. Or you could call it the latch state if you wanted to, right? It's latching on to previous bits or previous data. It's remembering bits from the past. Okay? See, the circuitry we were looking at before today, all the different combinational circuits we looked at earlier, didn't have this property. There's no way those circuits can hold on to previous data, previous bits. All right, so now the top 2 rows. Okay, the top 2 rows, S and R are both 0. and the next data Q is a 1. But this doesn't tell the whole story, okay? For the top 2 rows, this analysis circuit that gave us this truth table, it doesn't tell us everything. Okay, to get the whole story for the top 2 rows, we got to look at the actual circuit. Okay, this diagram right here. If S is 0 and R is 0, right? S is 1 input to this top NAND gate, and R is 1 input to this bottom NAND gate. Can you tell me what Q and not Q are going to equal if S and R are both 0? They're both 1, right? Because again, if one input to an AND gate is a 0, you don't have to know what the other input is. The output's going to be 1. Right? In fact, if you didn't know that, right? If you didn't know that if one input to a NAND gate is a 0, and it's going to give you a 1 out regardless what the other input is, you know, if you didn't know that, and you thought, oh, I got to know what this input is before I can get this output, you would get into a catch-22 situation, right? Because you'd be like, well, to know this input, to get this output, I need to know that output. But to know this output, I need to know this input. But to know this input, I need to know that output. But to know that output, I need to know that, you know, you get into like an infinite loop, right? So you see, that's where it's really useful to understand the truth table, right? Because you could drive yourself crazy if you didn't. But yeah, we get both outputs equal to 1. Do you see a problem with that based on definitions of Boolean algebra that we talked about earlier in the class?
Yeah, not Q shouldn't be the same as Q.
Right, exactly. Based on our definition in Boolean algebra, what this bar means, right? Remember the bar means opposite of. So if both Q and not Q are the same value, that goes against our definition of what not a variable means. So because when both inputs here are 0, it gives us outputs that don't agree with our definition of what the bar means in Boolean algebra. We call this the forbidden state. Okay. Sometimes it's also referred to as ambiguous state. All right. And again, forbidden, ambiguous, it just means that it goes against our definition of what not a variable means. You have a question?
Yeah, so then why are the story? Yeah, why is the storage for?
Say that again.
Why is the storage for?
Well,
Yeah.
remember how we got the storage? It came from these 2 rows that we got in the analysis. Yeah. Yeah. The only reason for this top row, you know, the forbidden state, we went to this diagram is just because the analysis circuit didn't give us the whole story. You know, it told us that the next state would be 1, but to see that both Q outputs are 1, you have to look at this. Yeah, that's all. So typically, you would avoid this. You know, you avoid the forbidden state, right? Because again, it just goes against our definition. How do you avoid it? Well, just make sure both inputs are never 0 at the same time. You see, this circuit exists because of the hold state, right? That's its unique feature, is the hold state. This forbidden state, it's just baggage that comes along with this circuit, okay? And the latch, okay, your basic latch, that was the first logic circuit that had this property of memory. But later on, they made an improvement. Okay, they came up with what's called a flip-flop, okay, which is also a memory circuit, but it has improvements over the latch. Okay, and we're going to talk about what those improvements. Okay, but yeah, the key thing at this point is just understanding what we mean by storage of data, which again just means that the next state of Q is going to equal the present state of Q. That means you have storage. All right, I got to move the camera. All right, so any questions up to this point before we start talking about a flip-flop? Get my view here. That's where we want to be. All right. Okay, a flip flop. It's a edge sensitive latch. Okay, and I'm gonna explain what's meant by that. Okay, but that's the definition of a flip flop. It's an edge sensitive latch. Now, on each table, excuse me, on each table, there's this handout. And if you take a look at this handout in the upper left-hand corner, this is the logic circuit of a D flip-flop. Okay, there's different kinds of flip-flops, but the most common and the one we cover in this class is the D flip-flop. So take a look at this logic circuit. Is there something in that logic circuit we've already talked about today? Yeah, see right there, there's cross-coupled NAND. It's exactly this right here. So you see the flip-flop has the latch, plus it has additional gates, right? There's two other NAND gates and there's a NOT gate. Well, that additional logic, right? The additional two NAND gates and NOT gate, that's what gives this edge sensitivity. Okay. Now, I could spend the next 20 to 30 minutes explaining how those additional gates give the edge sensitivity. But I've chosen instead to refer you to a video that I posted on Canvas under this meeting that does a much better job than how I could explain it on a whiteboard. And it does it in about, 12 minutes or so. Okay, because it's a video that uses some animation and it just does a better job, in my opinion, of explaining the edge sensitivity than what I could do in 20 to 30 minutes on a whiteboard, and not as well. Okay, so I'm just going to refer you to that video if you want to see the details on how that additional circuitry gives the edge sensitivity. I'm going to jump right into how the D flip-flops operate. Okay. Okay, so these are the symbols for the two different types of D flip-flops that we have. So D and CLK. CLK is short for clock. And these are the inputs. And Q and not Q are the outputs. That's actually pretty standard that all flip-flops have their outputs labeled as Q and not Q. The triangle right here on the clock input, that identifies that they're edge sensitive. And again, I'm going to talk about what's meant by that. Now, when you look at these two symbols, can you see there's a slight difference between the two? Do you see what's different? What's different? Yeah, it's got this little bubble. If it doesn't have the bubble on the clock input, then this is called a rising edge trigger D flip-flop. So rising edge trigger. And if it's got the bubble, it's a falling edge trigger. Okay, not field effect transistor like in electronics. Okay, you have electronics, FET has a different meaning than electronic stuff. In a logic class, it's falling edge trigger. Now, how many people have used an oscilloscope? Okay, a lot of, yeah, if you're an EE, I would think you've used an oscilloscope before. Have you heard of positive edge or leading edge? Yeah, positive edge, leading edge is the same thing as rising edge. Have you heard of negative edge, trailing edge? Yeah, negative edge, trailing edge is the same as falling edge. See, rising edge in this case refers to a transition from 0 to 1. So if you have a square wave, at the time it transitions from a 0 to 1, that's the rising edge. Okay, and you can probably guess what a falling edge is, right? It's just the opposite. falling edge is the time at which a digital signal goes from a 1 to a 0. Okay? All right, so the next thing is I'm going to fill out these truth tables for both types. So I'm going to go ahead and fill it out, and then I'll explain, once I have it filled out. So let's see that 0, 0, 1. It's the arrows going up. And then this would be 0, 0, 1. Here, 0, 0, 1. Okay, so when you look at these truth tables, you'll see that they're identical, except the clock has an arrow going up for the rising edge, and the clock has an arrow going down for the falling edge. Well, the reason why you see an arrow going up for the clock for the rising edge is because that arrow is symbolic for this transition from 0 to 1, and this downward arrow is symbolic for a transition going 1 to 0. Okay? Now, if you split these truth tables in half, what they tell us is when the D input is a 0, doesn't matter what the present Q value is, the next state of Q is going to be a 0. Okay? And it's going to happen at the time of the 0 to 1 transition of the clock. Okay? If the D input is a 1, it doesn't matter what the present value of Q is. At the time of the 0 to 1 transition of the clock, the next state of Q is going to be 1. Okay? And the table for the falling edge trigger D flip-flop tells us the same thing. The only thing that's different is that it's going to happen during the 1 to 0 transition of the clock instead of the 0 to 1 transition. That's the only difference between the two. Okay? So the way you can sum up, how a D flip-flop works in words is that the next state of Q will equal input D at the time of the appropriate clock transition. Otherwise, the next state of Q will just equal the present state of Q. And you see what I mean by appropriate is that if you have a rising edge, next state of Q will equal D at the time of the 0 to 1 transition of the clock. Otherwise, next state of Q just equals present state of Q. If you have a falling edge, well, then it's next state of Q equals input D at the time of the 1 to 0 transition of the clock. Otherwise, next state of Q just equals present state of Q. Okay, do you have a question? You look like you have a question.
Get what you said?
Okay, well, let's take it one by one here. See, if we have this type of D flip-flop, if the D input's a 0, at the time of the 0 to 1 transition of the clock, the next state of Q is going to be 0. See, it's going to equal D. If D is 1, at the time of the 0 to 1 transition of the clock, the next state of Q is going to be 1. So again, next state of Q equals D. So you see, I'm just summing it up. I'm just saying next state of Q will equal input D at the time of the appropriate clock transition, because here the appropriate time is the 0 to 1 transition. Here the appropriate time is the 1 to 0 transition. So both types of the D flip-flops have this property. The only thing that's different is one happens on the rising edge of the clock and the other one happens on the falling edge of the clock. That's the only difference between the two. And then, you know, if you don't have this, right, so for all other time other than that appropriate transition to the clock, the next data queue is just gonna be whatever it was before. It's gonna be equal to the present state of time.
So on the rising edge, if it's going from 1 to 0, it's not gonna.
Correct. Yeah. And likewise, over here, it's not gonna change on a 0 to 1 transition. Yeah. So my next question to you is, when does a D flip-flop store data? Does a D flip-flop store data at the time of the appropriate clock transition when the next data queue would equal whatever the D input is? Or does a D flip-flop store data for all other time other than the appropriate clock transition when next data queue equals present state of queue? When is this flip-flop storing data? All other time, right? Because like we said earlier, if your next data queue, right, if your future state of queue is the same as what queue was, that means you retain previous bits, right? You retain previous information. See, the only possible time that Q can change is at the time of appropriate clock transition, because then it could equal D, which could be a different value than what the present value is. Okay, so flip-flops, they're storing data for all other time other than the appropriate transition of the clock.
So I don't really get the arrow thing on the CLK, like what data is that? Is it an input? Is like,
No. What the arrow symbolizes, the upward arrow symbolizes the time that this happens. The time that the clock goes from a 0 to a 1. See, just like I wrote an arrow on the transition, you know, there's an arrow that's just representing that time. And again, the downward arrow is just representing the time that the clock transitions from a 1 to a 0. See, that's the edge sensitivity. The edge sensitivity is that, you know, this next data Q is going to equal whatever input D is only on a transition, you know, only on an edge. See, and again, what gives that, you know, what makes it edge sensitive is that additional couple of gates there, additional mitigation with not gate. Okay. See, the latch by itself, right? The latch by itself, its outputs are determined by levels, right? There's no edge sensitivity with a latch by itself. Okay, see, this was like the original memory circuit, if you will, that was dependent on level. And then they came up with a flip-flop later on that included this edge sensitivity feature. Okay, so you still have the memory, but in addition, you have some advantages because of the edge sensitivity. Like the flip-flop has advantages over the latch that I'm going to get to in just a second, because of that edge sensitivity. Okay. All right, and what those, let's see, am I still in view here, John? What those advantages are is, first of all, do you see any forbidden state here? Do you see any Q equaling not Q in this truth table? No. See, that's one advantage. A flip-flop doesn't have a forbidden state in its truth table like a latch does. So you see there's no forbidden state. And, you know, that's an advantage just because you don't have to worry about it. Like with the latch, you know, you like to avoid it. So again, you just got to be concerned that these two inputs aren't the same value to give you that forbidden output. So here you don't have to worry about that. Now, having said that, there is another scenario where a flip-flop can give you an ambiguous situation. It's just not in its truth table. Okay, when we look at a timing diagram, I'll show you an example of where you can have an ambiguous situation. Okay, the second advantage that flip-flops have over latches is that they're less susceptible. Who's a good speller? Is it CIDL? Is that right? Who's a good speller? Susceptible, is it I or A? It's not, okay, thank you. So flip-flops are less susceptible to noise. All right, so when I asked if anyone had, used an oscilloscope, almost everybody raised their hand. So when you look at an oscilloscope and you see a waveform, right? And as you know, oscilloscopes show voltage versus time, right? So you're looking at voltage waveform. Are those waveforms typically nice and clean and crisp, or do they tend to be fuzzy a lot of times? Yes. And you know what that fuzziness is, right? That's the noise, right? And if you were to zoom in on a real fuzzy type of waveform, I don't know if you've ever done this, but you change your settings and you really zoom in on it, you would see that fuzziness is a bunch of spikes, like voltage spikes. Okay. So noise is voltage spikes. And as we've talked about before, now granted, we didn't spend a whole lot of time on it, but there was a couple of times where we talked about how, ideally a 0 is like 0 volts and a 1 is like, plus 5 volts. But in reality, because voltage fluctuates, a 1 is a voltage above a certain amount, like 1.4 volts, and a 0 is a voltage below that same threshold, we call it 1.4 volts. Well, if you have a noisy signal, and you have something like a latch that depends on voltage levels, it could very easily, some noise, a voltage spike, could very easily change a 0 to a 1 or a 1 to a 0, right? Because say you had a 0 and you got a voltage spike in the positive direction, well, that 0 voltage could go from something below the threshold of 1.4 to something above. And when that happens, it's now being read as a 1 instead of a 0. And that can change everything after that, and it can make your circuit not work the way you want. Or the opposite can happen, right? You can get a voltage spike in the negative direction and have a 1 that turns into a 0. Okay? Well, because flip-flops are edge sensitive, right? That a change in the output is only going to take place at the time of either the 0 to 1 transition or 1 to 0 transition, depending on which type of D flip-flop you have. Well, it's much less susceptible to noise because the voltage spike would have to happen at that time of that transition, right? If it happens at a different time other than a transition, it's less likely to affect things, okay? So the edge sensitivity of a flip-flop, that's what makes it less susceptible to noise compared to a latch, which is level sensitive. Okay, now again, it's not that they're, flip-flops are not 100% immune from noise. They can still be affected by noise, but again, it's less so compared to a latch. Okay. All right, let's see. How are we doing on time? Okay, we're at the top of the hour. I know it's going to take me another at least 30 minutes to finish this. So let's take a 5-minute break till 5 past, and then I'll pick up with this because I don't want to rush through the remainder because the activity you have today has to do with timing diagrams involving, or a lot like this example I'm going to do. So I just want to make sure you're fresh when I go through this. So let's take a 5-minute break and I'll start up again at 5 past.
Yeah. So, we go. Goes back to it, so, last point.
I mean, sorry.
This close.
Where'd you go to?
I almost have a working sim. Yeah, 2 test cases are wrong. I was gone a day.
I procrastinated.
That's.
Yeah, I didn't do it. I became keyboard descriptive.
Doing everything. It's really.
You just have a. That you can get.
What the?
You have to that.
I just did
Whenever place has like particular like food markets, it has those like tiny fruit flies, those things always fly that case and those.
Yeah.
For this battery that's out. And then you have to do it. Yeah, I just. Oh, I think we need. Yeah.
Pitchforks. That's the big.
But I got to do this. Correct. Yeah, I am not ready. Right.
I.
Testing is what. And then reason all of that. Good for it. If you're not. So. You just get easy. Please. So I'm scared it's gonna be exactly the same, just like that is to be. Yeah, you change the.
Step but that is how you. Or,
You're gonna need spell one.
like, so, for example,
They're along.
when you have a.
Some ways like.
Reluctant is. Stationary, technology, some road stationary. But moves it when it's AC. What they'll do is they supply DC. For a series of cabinet, I guarantee that.
Very
Similar. Repay like step. It's got to be done. Where like step it down, like the shape of the line. And then like not AC, it's like. But it all, like. I stepped it down.
I don't know.
Like,
I mean, I know people in
an AC. That's how we installed the rods that you do.
I learned.
Because if you just like turn the power off, the motor will unlatch. And you just don't want it gets shut down. But so you need to go, you need to pull in, it'll move
they would have like chip in, and they would.
Oh, we'll get plenty of AC.
Yeah, yes, it's a-
And too, you guys haven't gotten there yet, it's about
It's like Carolina.
like the, that's. This is the tea house.
So. Like spread.
Oh,
Just like I did.
did you know that?
Just heard it's like. Yes, I think. I can. So many people. I work for one.
Hell yeah.
Well, I was there. I was there. They got GDA. I got.
That's so. Like everything else.
Most of you, of course.
Maybe the road.
That was in here. Okay, so let's go ahead and finish this up today. Okay, so these two symbols of the D flip flop, these are your basic D flip flops that just have a D input and a clock input. But often flip flops will have additional inputs. Okay, often they'll have what's called an enable. And enable goes by a couple of other names also. Okay, sometimes instead of enable, they call it load, or they call it enter. And then also often you'll have an input reset. Reset is the same thing as clear. And then also often you'll have an input called set. Okay. So if you have an enable input, it will typically look like this. Or it could look like this. It has a little bubble, and I'll explain what the bubble means a little later. But when that input is activated, and I'll explain, how you activate it. But if you have enable, when it's activated, then this will happen, that the next data Q will equal whatever the D input is at the time of the appropriate clock transition. Okay, so the enable is like an added condition to this. Okay, if you don't have an enable, then this is going to happen regardless. Okay, but if you have an enable, it has to be activated for this to happen. Could you guys not talk so loud? It's carrying up here. Thanks. Now, reset, if it's activated, Q is going to equal 0. Okay, we think of reset as sort of being like a dominant input, that when it's activated, it takes over, and now like the D input doesn't matter anymore, and Q is just going to equal 0. In fact, reset most often is the highest priority. Okay, set, when it's activated, it's going to make Q equal to 1. And set is normally the second highest priority. Okay? All right, so now, how do we activate these? Oh, also, let me show you on the diagram. If you have a set, it could look like this. Usually it's just an S, or it can have the little bubble. And reset, normally you'll see it like this. And again, it can have a little bubble. I'll explain what the bubble means coming up in just a moment. Okay. All right, well, how you activate these inputs, there's two ways you can do it. You can either do it with a 0 or you can do it with a 1. If a 0 activates it, it's called active low. Okay, so active low 0 activates. Activates input. And if it's active high, a 1 activates the input. Okay, so, if you have an active low reset, you would have to put a 0 on that reset input. And if you put a 0 on that active low reset input, that would make it reset. That would make Q go to 0. If it's active low and you put a 1, it's not gonna reset. Okay, and if you had an active high set, well, you'd have to put a 1 on that set input to get Q to be a 1. Okay, and in a diagram, if there's no bubble, it means that that input is active high. If there is a bubble, it means that that input is an active low. All right, so you see here, all these, the S, enable, and R, those would be active high. Here, the S, enable, and R reset would be active low. Okay, so any questions on that?
The bubble is high.
No, the bubble would indicate active low. Yeah, and no bubble indicates active high. Now, that's if it's in the diagram. Sometimes, like in the activity that you have today, I tell you, I just write it out when it is. And sometimes if the diagram doesn't show it, you might have to look at like a manufacturer catalog for that particular flip-flop and see what it is. Okay, so the next thing is each one of these inputs, enable, reset, and set, can either be synchronous or asynchronous. Synchronous means it depends on the clock. Asynchronous means does not depend on the clock. And I think the easiest way to see the difference is with the timing diagram. And, each one of these, the enable, the reset, the set, each one of them can be synchronous, each one of them can be asynchronous. And same thing with the active low, active high. Like each one of these 3 inputs can either be active low or active high. Okay. All right, so let's do a timing diagram example. And this is what the activity is like. I give you 6 timing diagrams for a D flip-flop, and I give you different combinations of active low and synchronous and asynchronous. I give you some that are rising edge trigger, and I give you some that are falling edge trigger. Now, all of them have enable equal to 1. And now I could have, written here EN, just showed a waveform 1 all the time, but just to save some space, I just decided to do it this way. Okay. All right. So first thing, in a timing diagram, and I know this is confusing, but this is just the way it is. Don't shoot the messenger. Okay, I didn't make this up. In a timing diagram, a bar over a symbol doesn't mean opposite of. Like this doesn't mean that if you flip this waveform, it's now R. Okay. What the bar over a variable means in a timing diagram is active low. All right, so you see this is an active low reset, active low set. If it was active high, it wouldn't have a bar. Okay, but we're making these active low. Okay, so we got our reset, our set, here's our D input, here's our clock. And we're gonna find what the Q output is. Now notice I didn't put a not Q. The reason I didn't put a not Q is because since the D flip-flop doesn't have a forbidden state in its truth table, right? There's no case of not Q not being the opposite of Q. Once we find Q, if we wanted not Q, we would just invert Q. Okay, now you can't do that for a latch, right? Because the latch, you would have to show both Q and not Q, because it's possible Q and not Q be the same if you don't avoid the forbidden state. Okay, so like any timing diagram, you start at t equal to 0, way to the left. Now, at t equal to 0, Q is either going to be a 0 or a 1, and you don't know which, unless you're resetting or setting, or you have an appropriate edge of the clock right at t equal to 0. Right now here, this is a rising edge. So that's why I put arrows on each of the 0, 1 transitions, right? Because it's rising edge, anything that's synchronous, or if we have this case here where D is going to give us the value of the next state of Q, well, that's going to happen on a rising edge of the clock. Okay, the 1 to 0 transitions don't matter in this case, right? Because we got rising edge. So if you look at this active low reset is high at t equals 0. This active low set is also high at t equals 0. And we don't have a rising edge of the clock at t equals 0. So because of that, we don't know what Q is initially. I mean, it has to be either a 0 or 1. That's the only two possibilities. But we don't know what it is. So the best way to show that you don't know the value of Q, in my opinion, is just to put an X or a question mark. Okay? Now, having said this, when you look at the solution for the activity, you're going to see that there's cases like this where you don't know what the value of Q is to start with, but instead of an X, you're just going to see a value of 0. And that's because the person who made up the solution for the activity is assuming that it's starting at 0, even though they don't really know. So you could do that. You could just assume a value, either 0 or 1, but if you did that, you should specifically say, you know, I'm assuming this value, even though I don't really know what the value is. Okay, I don't particularly like that in the solution. You know, I like this better because this really tells what's going on. You don't know. Okay. All right. So the next thing that happens, the next thing that changes in this timing diagram, and you know, you're working your way to the right, right? T equals 0. As you go to the right, time is progressing. So the first thing that happens that changes is this reset. This active low reset goes from a 1 to a 0 at this time. Okay, so this is a synchronous reset, which depends on the clock, right? If it's a synchronous input, it depends on the clock. And you see what that means is that for the reset to happen, it's not enough that it equals its active value. It has to equal that active value at the time of a rising edge of the clock. So you see, when that reset goes to a 0, Q's not going to go to 0 yet. See, it won't go to 0 until we have the active value of reset at the time of the rising edge of the clock. So you see, it's going to remain unknown. You know, I'm not going to know what the Q output is until this time right here. Then I can say it's a 0, because then the reset will happen. Okay, the asynchronous reset will happen when it's at its active value, which is 0 in this case, at the time of the rising edge of the clock. See, if this was an asynchronous reset, once the reset becomes its active value, so right at this time, that's when it would reset, right? Because an asynchronous input does not depend on the clock. Okay, so for an asynchronous reset, Q would go to 0 here. For a synchronous reset, Q doesn't go to 0 until here. Okay, see, that's the difference between the two, right? Asynchronous, you don't even care about the clock. Synchronous, it's got to be the active value at the time of the appropriate clock transition, which is rising edge in this case, in order for the reset to happen. Okay, so any questions on that? Because if you understand the difference here for this active low synchronous reset and any synchronous input, it's the same thing. Okay. All right. So the next thing, let's see, what's the next thing that happens? Well, the other thing is, once the output goes to 0 because of this synchronous reset, it's going to stay 0 until something changes it. Okay. You know, at this time here, where this active low reset goes back to high, Q is still going to be 0. Okay, something has to change it for Q to change. Okay, so let's see, what's the next thing that happens? Okay, so the next thing is, well, this is the approach you take when you're doing these timing diagrams, is you first look to see if reset is active, right? So you see, once reset goes high here, reset's no longer active, then look to see if set is active. Well, during this time, set is not active because it's also active low. So if you're not resetting and you're not setting, then the Q output is going to be determined by what the D input is. Okay? So in the D input will equal the next data Q only at the time of an appropriate edge of the clock, which again is rising edge in this case. So the Q output, it's going to stay 0. Right? It'll be 0 all this time until this positive edge of the clock. At this time of the positive edge of the clock, Q is going to equal the D value, which is 1. So Q is going to go up to a 1. It's going to be unknown for this amount of time. Then it's going to go to a 0. It'll stay at 0 until this transition of the clock. And then it becomes equal to the D value of 1. Okay, and it's going to stay a 1 until we get here to this rising edge. And at the time of this rising edge, and again, we're not resetting, we're not setting, so D is going to determine what Q is, and it's at the time of the rising edge, that value of D is what's going to determine Q. So you see how D is at 0? So at this time, Q would go to a 0. Okay, so all right up to this point. Okay, next thing, right here, okay, and I meant to make these exactly lined up. I mean, they might not be exactly lined up, but my intent was to make this rising edge of this clock here line up with where R is changing from a 1 to 0. So let's say this was exactly, this transition of the reset going from a 1 to a 0 is that exactly the same time that this rising edge is going from 0 to 1. Okay, so you see this reset input is changing at the same time as this appropriate edge of the clock. Can you see a problem with this? Do you see a problem?
It's unknown. It's kind of just like a flip of the coin on whichever signal is
Exactly, yes.
first.
Right, exactly. Because this change in input is happening right at the same time as this clock transition, and R is synchronous, so it depends on the clock. We don't know if it's going to be a 1 or a 0. Right? Like you said, it's a flip of a coin whether it's going to be a 1 or a 0, because that change in the input, that synchronous input, is occurring at the same time as the clock edge. Right? So that you see there's ambiguity there. So, that's what I meant when I said, well, there's no ambiguous state or no forbidden state in the truth table of a flip-flop, but you can still have an ambiguous situation, right? And that ambiguous situation is if you have a synchronous input that changes its value at the same time as the appropriate edge of the clock, you don't know what the output's going to be. I mean, it's going to be either a 0 or 1, but you don't know which one. Like Tyler said, flip a coin. Okay, so you want to avoid something like this, like in your final project or any of the labs that have sequential circuitry, or in CP233 when you build that microprocessor that has sequential circuitry. If you come across a waveform and it looks like this, your design is probably not working 100% of the time. Like it may work 50% of the time. All right. So yeah, you want to avoid situations like this. So yeah, this would just be a question mark or an X. We don't know. At this point, we wouldn't know what the output is. It could be either a 0 or a 1. We don't know. Okay. Let's see. The next thing that happens. So we're just going to say an X here. Okay. The next thing that changes is this set, this active low set, which is asynchronous. it goes from a 1 to a 0, right here at this time. So since it's asynchronous, what does that mean? Doesn't depend on the clock. So if it's asynchronous, all it takes is for it to go to its active value, right? The clock doesn't matter. So as soon as that asynchronous goes low, which activates it, it's gonna set. So it's gonna go from some unknown value, either a 0 or 1, but unknown. And what's it gonna become since it's setting? Because what does set mean? It's gonna go to 1. Okay, it'll go to 1. Okay. All right. Oh, and then actually here, let's see, there will be a 1. But then you see this set is going to 1 before this clock edge. I mean, it's kind of close. Actually, let me move this a little over just to make it more pronounced. We'll move this over a little bit. Okay, so it's gonna set. But then right here, set is no longer activated and reset's not activated. So Q is going to depend on D. And Q will equal D on this rising edge here, where D is 0. So right here, it would go back to 0. And it would stay 0 until we got up to here, right? Because then the asynchronous set goes back to 0, so it's activated, so it'll go back to 1. Okay, so the activity, there's 6 timing diagrams where, some of them are rising edge, some of them are falling edge. I give you mixtures of active low, active high, asynchronous, synchronous. Okay, but the process is the same as what we did here. Now, one other thing is that in the solution, and again, I didn't do the solution for this activity, another person did, and what that person did, which I don't like, is that in a situation like this, where you have an ambiguous, right, where the change in inputs occurring, the change in synchronous input is happening at the same time as the clock edge. What they did in the solution is they took the value of the input before the clock transition. So like in a case like this, they took it as R was 1, so the reset didn't happen because it wasn't activated. But I don't like that because, again, it's really this, that it's an ambiguous case. So again, if you run into this in this class, when we get into sequential designs, or like I said in 233, you definitely don't want to have this. Okay, but for the purposes of the activity, when you look at the solution, you're going to see, you're not going to see an X here, you'll see some value, but I'd rather you put the X. All right, so any questions about this before we move on? I want to show you the system Verilog code that you're going to need for Lab 5, because Lab 5 does have a D flip-flop that has an enable, a reset, and a set. Okay, it's got all those inputs, because basically Lab 5 is Lab 4 with memory. Okay, you're going to take most of what you did for Lab 4. I mean, there's a few modules that you're not going to need, but a lot of what you did in Lab 4, you need for Lab 5, and then you're going to add memory to it. You're going to add 2 D flip-flops, and you're going to add something called a register that we're going to talk about Tuesday after the midterm. And then we're going to give you some code that Dr. Mealy designed that models a time multiplexer. And with the time multiplexer, you'll be able to use all the 7-segment displays. You'll be able to put, light up multiple displays and show data. Okay, but we'll talk more about that on Tuesday. But for right now, let me show you how to model a D flip-flop that has, the D input, the clock input, enable, set, reset, along with the Q output. So like any module, you'll have to give it a name. I call it DFF. And then you got to declare the inputs and outputs as you've done. So again, there's going to be 5 inputs. Okay, they're all single bit. B, enable, clock, set and reset, two outputs, Q and not Q. Again, everything's single bit. Now, we're going to use an if statement to model the flip-flop, the D flip-flop. You used an if statement to model the mux. And do you remember what block, the name of the block that the if statement had to go within for the mux?
Always counts.
Yeah, always comb, right? The COMB, because a mux doesn't have memory, it's combinational. So that's what the COMB means. Well, since this is sequential, when you use an if statement, it has to go within a different block. And that block is called always FF. Always underscore FF. And then you put the at symbol. And then in parentheses, we put what's called a sensitivity list. Just like the case statement has a sensitivity list, where what goes within that parentheses, when it changes, that's when the if statement gets evaluated. And we want to make our D flip-flop, we want to make it rising edge, okay, a rising edge trigger. So the way you do that in System Verilog is within the parentheses, you put positive edge or pause edge clock. Okay, so what that means is that on every 0 to 1 transition of the clock, what's inside this always FF is going to be evaluated. Okay. All right. So then we need a begin. Okay. And then we're going to start the if statement. Now, I've been noticing, people with their if statement, if the condition is, something's going to be high, they'll put, well, like, for example, we're going to make our reset. In fact, we're going to make all these inputs active high. Okay, so reset, set, and enable, they're all going to be active high, and they're all going to be synchronous. Okay. So in the if statement, we're going to start with the reset because we want to make the reset the highest priority. Okay, so whatever you put first in your if statement, that's the highest priority because that will get evaluated first. Okay, so I'm going to do if reset. Now, you could also put reset 2 equal signs 1, but this works also, right? Because it will just take this and if it evaluates it true, right? If you just put reset, it's going to see if reset's equal to 1. And if that's true, then whatever you have for your under your if is going to happen. And what we would want to happen since we want to reset is we want to make Q equal to 0. Now notice, instead of just using an equal sign, I use an arrow symbol, and this would be made with the less than along with the equal sign. And that's because when you're within an always FF, you have to assign outputs like this using this symbol, again, the less than with the equal sign, which is called non-blocking. Okay, so this is for always FF. When you're doing always comb, like you have been doing, that's when you use what's called blocking, which is the equal sign. Okay, so within an always comb, you have to use an equal sign when you're assigning the output to a value. When you're in an always FF, you use the less than in the equal sign to assign an output value. Okay, see, the reason for this is because if you had code, within an always comb, where you have B equal A, and then right after that, C equal to B, well, this would make, A equal to C. Okay, because when you use the blocking, what's going to happen is that A, B, and C are just going to be connected with a wire. Okay, with the blocking assignment, you would just make all these the same node, right? So they all would be equal. But if you did the same thing in a non-blocking case, right, within an always FF, where we use the less than with the equal, well, if you did B assigned to A and then C assigned to B, okay, same as what we did over here, but with the non-blocking symbol, A, B, and C are not going to be the same thing because what's going to happen is that there's going to be circuitry in between A, B, and C. They're not gonna be connected to the same node. You know, there's gonna be logic circuitry, you know, essentially latches put in. So this is important to know. Okay, so A will not equal C in this case. It equals C in this case. So the reason this is important to know is because if you have an always FF block and you just use the equal sign, you're likely not to have the memory that you're looking for. Okay, and you'll either get errors or the circuit's not going to work the way you intended. And likewise, if you have an always comb and you use the less than with the equal, right? You use the non-blocking instead of the blocking. Well, now you're going to have a combinational circuit that probably has memory in it. So you're going to get unintended latches. Okay, so that's why you have to be careful with, you know, which symbols you use here. Okay, but getting back to this, so this would be for an active high reset. If you had an active low reset, the only thing you would have to do different is you'd put an exclamation point in front of reset, and that would make it active low. Okay, so the exclamation point within a sensitivity list of an if statement is the same as like a tilde in a Boolean expression. Okay, but we want it to be active high, so we're not going to have the exclamation point. I just put that there just so you know how to do an active low if you needed to.
After the if reset up again.
No, you're talking about right here at begin?
Yes.
Yeah, the reason you don't need one is because we only have one output. If you have multiple outputs, then you have to put begin end. Okay, but if you have a single output, you don't need it. If you go back and you look, when I talked about the if statement before you did the mux, you know, I had the example of a comparator. And the comparator had 3 outputs. It had, you know, greater than, less than, and equal to. And because it had 3 outputs, that's why I did a begin end in that example. But then you also might remember that after I, you know, did like the initial example of the comparator with the 3 outputs, I did another example where I initialized all the 3 outputs to 0. And then because I had initialized the outputs to begin with, and only one of the outputs was changing, you know, for each condition, you know, I didn't have to use the begin end. So when you have multiple outputs, if only one of them is changing based on some condition in your if you initialize them all to 0 or some value to begin with, then you can get around the begin end, because as long as you only have one output changing in the if, you don't need the begin end. So, was there another question? I thought I saw it. Yeah.
What's the character after all this?
Oh, that's an at symbol. Sorry, it's the at symbol.
Okay, and then is there a space for okay or no?
Oh, you know, I think there is a space, but the way you'll be sure is that it turns a color. It turns like a violet color.
So pause edge, CLK means like taking the, if we're starting the clock on a positive.
Well,
Rising actually on a
well, whatever you put within the parentheses, when that changes, that's when the always FF block will be evaluated. So that's when the if will be evaluated. So the pause edge is referring to the 0-1 transition of the clock. It's referring to the rising edge. So that means on every rising edge, this if statement is going to be evaluated. And that's what we want, right? Because, you know, we're making a rising edge trigger flip-flop. Yeah, I mean, if it was a falling edge trigger, we would use neg edge. Instead of pause edge, you'd have neg edge. And that would refer to the falling edge of the clock.
okay.
Okay?
Thank you.
Yeah, sure. Okay, so going on here, that's the reset. The next thing is we'd have an else if for the set, because we want to make set the second priority. And we're also making it active high. So if we're not resetting and we're setting, that's going to make Q equal to 1, right? Because that's what set means. Okay, if we're not resetting, we're not setting. See, this coding for modeling the D flip-flop is just how you approach doing a timing diagram manually, right? You always look to see, well, is it resetting? Is it setting? right? And it's not doing those two things. Well, now Q is going to depend on D. All right, so then you'd have an else if. And this is where the enable comes in. Right, because if it's enabled, then we're going to assign Q to D. So this would be Q assigned to D. Okay, so you see we got an if, we got an else if, we got an else if. Now, when you did your mux, now the mux didn't require any else ifs, right? It was just if, and then what did you end the mux with? An else, okay? And you might recall at that time, I said that if you have a combinational circuit like the mux, the comparator, or any other combinational circuit that you use an if statement with, you always want to end it with an else, because if you don't, what happens? Do you remember what happens? Errors. Well, you won't get errors necessarily. You'll get a warning though. You'll get a warning with a word that we said to treat like an error. Yeah, see, if you don't have an else to an if statement, it creates a latch. Well, that's what we want here, right? Because if we're not resetting, if we're not setting, and if we're not enabling, right, where next data Q is going to equal D, well, then we just want the output to stay the same as what it was, which is storage. Okay, so when you want a latch, one way to do it is don't end your if statement with an else. So you intentionally don't have an else. Okay, so I'm doing 2 backslashes because that's what you do in System Verilog to make a comment, right? So, you know, you purposely have no else to create a latch, right? Which is memory. Because in this case, you want the next state of Q just be equal Q. Okay, you want storage. Okay, and then you would just end your begin and then end the mock. Okay, so I've given you the code. Now, when you look at this handout, the handout that has a diagram that shows the sensitivities logic you need to make the flip-flop, there's also a bunch of examples of different code for different flip-flops, like the basic flip-flop that just has a D input and a Q output. It has a D input, a clock input along with the Q output. You know, then there's one with just an enable. You know, there's one that shows you how to do an asynchronous reset and so on. You know, I provided those just, you know, for reference. But this is the one you need for Lab 5. You know, you just have to put in, you know, declare the inputs and outputs. Now, here's another review question. When you did the always comb, whether it was an if statement or a case statement, right? Whether it was your mux or your decoder, do you remember there was something additional you had to declare for your output that was within the always comb? Like if you have an output within an always comb, there's something you have to add in the declaration of the output.
Output logic.
All right, you got to put output logic, right? Same thing with an always FF. Any output within an always FF, you've got to have that logic there. So like when you declare Q, you got to put output logic Q. Okay. So I would definitely, you know, at some point before you leave today, I would definitely take a picture of this, right? Because I've basically given what you need for the D flip-flop of Lab 5. And, you know, I imagine everyone's still working on Lab 4, which, you know, that's what you should be doing, because that's the next one due after the midterm next week. But Lab 5 will be due the week after next. Okay, so if you get ahead of things, you know, you could start on that if you wanted to, once you're done with Lab 4. And once you prepare for the midterm. Okay, so do you have any questions before you get going with the activity? That's the next thing to do the activity. And then after that, it's up to you what you want to do after that. So, okay, all right.